have going down and up and down, so you have two cross-section points. All right, but the thermal, that's the property of the motions. The same thing in your in that field matrix. So if you look at that, this is my zero line. The first mode is all down, and this is my x. The second mode is then the down and up. So I have one cross section. The third mode is down, up, and then down. So I have two cross sections. See? So if I ask the fourth mode, how many cross sections points do you have? The third mode I have two. The fourth mode I have how many? The fourth mode I have three. The fifth mode I have four, and so on. Okay. So this is the property of this. So that's what we call monocoordinates. See, this is all the monocoordinates things. And all the W here, this is all the monocoordinate. So the W will be all the mode shape added together, just like what we did in our frequent response functions. Okay, this is a summation of k equal 1 and this is your physical coordinate is nothing but your motor coordinates times your mode shape. This is a motor coordinate Q times your mode shapes. So that's exactly the same what happens in the PDE or in the matrix equations. Okay, now I'm going to skip those. Because this is a lot of things going on here. I just don't have time to talk about it. Although you might use it later on, but in our class here, we're not going to talk about PDE control. Okay, so I'm going to skip those. Okay, I'm going to skip those, and I'm going to show you some pretty pictures here. Look at this is the first bending. This the first torsion. This first vertical modes. The second lateral bending. Look at this. The second torsion. This is second vertical bending. Your physical bending or torsion, your physical bending will be like a first bending, second bending, and third bending added together, and weighted by the Q. The same thing, first torsion, second torsion, and torsion mode will be all this added together. In analysis, vibration analysis or control analysis, sometimes will show them this kind of the motion, so they have some feeling. In other words, that like all earthquake, most likely all earthquake come in will be like maybe this kind of motion, that kind of motions, or that kind of motion, that kind of motion can be two directions, this motion or that motion, and building will move like this. If building move like this, that means the first bending. All right. So if your earthquake coming frequencies is the same as your first bending frequencies, then your motion will be like this. Your earthquake coming to the to excite the building is the second bending frequencies, and your building will be excited like a second building frequencies. So depending on what frequencies close to your earthquake frequencies, and that frequencies may be able to seen from your building if your building happen to have a mold shape in that frequencies. If your building, if earthquake coming is say 5 hertz, but I don't have 5 hertz mold shapes for this building, then it could be the combination of first mode and second mode and third mode and so on. But that we really don't concern much for those combinations. We concern that your some mode frequencies happen to be exact the same as the earthquake frequency or very close to earthquake frequency, and that is the frequency you can worry about it. So, for example, if this is 101, the first mode shape, and its frequency is 5 hertz. Now, if there is an earthquake frequencies happen to be 5 hertz and hit the Taipei city, the 101 building will be exact like this. Okay. And that will oscillate. The building is oscillate with the earthquake frequency, and that is dangerous. So when you design the 101, you might want to avoid those possible earthquake frequencies. Like you want to avoid all the frequencies less than 15 hertz. You want to design a building all higher than 15 hertz, then you at least you don't worry about the earthquake in Taiwan. But unfortunately, if there is an earthquake, it never happened in Taiwan before, but it happened once, happened to be in 20 hertz, then you are out of luck. Okay. But that's going to be very, very rare cases. So that is the mold shapes we are talking about here. In the matrix, the sensing, you will be able to see some mold shape like this, but it won't be like continuous like this. Okay? All right. That's the vibrations, and this is the wave. This is more like what in the longitudinal motion, and that's the wave motion is like this. Okay. Well, I think let me just conclude these chapters. This chapter talk about response of dynamic system. So I show you frequency response functions. That's one way to describe the response of a dynamic system. There's another way to show response of a dynamic system. That means like a mold shape I show you, the motion like that, all right? Or you saw the frequencies, saw the mold shapes. That's another way to describe the response of dynamic system. One is by frequency response functions, right? So we have two since here to we call to describe response of a dynamic system. So we introduce frequency response, right? Response functions. Right? We do this, and that's really most of the engineering applications use frequency response function to show how good of the design is. Another one, we also show you the monocomponents in terms of frequencies and the mold shapes. that's another way to describe the responses, because you know the frequencies, you know the mode shapes. On frequent response functions, they don't show you the mode shapes, but they show you the how much peak and how much damping you have. We also show you some of the PDE and how you describe a large system by a simple PDE formulations. And that's about these chapters, that's response. And next, from here, naturally, that we go to the, we call AVA. We're going to move to AVA. Okay. Now we are talking about real feedback control now. Okay. So this is the real feedback control. And we are going to talk about this called virtual passive controller. On TMD, the one basic property of TMD is you have to be, what is that? What is TMD? Do I use any power? TMD. Do I require any power? No. No power for TMD. Now, the control, all the active control require power. Now, we are going to talk about the real active control, which require power. Right, so I call virtual passive controller, and this is, I call the TMD with power. Another word is TMD with power. How can I have a feedback control which is limited to a TMD? All right. So, is there any, what do we mean a feedback control? Right. From here, we're going to talk about the feedback control. Yeah, we call active control. Okay. Now we're going to show you how can we design an active like a TMD. All right. Now, the disadvantage of TMD is every time you want to change the damper, but you have to replace the new damper, right? A different damper. If I find out my damping is not enough, how can I do it? I need to, like your motorcycle, how can I change my damper? You got to go to the shop, say, hey, I want to change my damper. Yeah. Check it out and then screw your damper and then put your new damper in there. Right? You want to do a better one. And the active is a little bit different from here. Right? Let us take 10 minutes off. This is 7 p.m. now. And we'll be back soon.